fun tonight. And yeah, weather on Earth can be pretty extreme, from heat to storms, tornadoes, hurricanes, lightning, thunder. But as you see, what happens on Earth is actually pales in comparison to what happens on other worlds throughout the cosmos. And this is where astronomy is really fascinating, because when you start to study even what's going on in our own solar system, just in our own backyard, you look at Venus, you look at Mars, our two adjacent worlds, just opposite ends of the spectrum, extremes compared to what's going on Earth. And then you go beyond our solar system. We're now just beginning to discover planets circling other stars, exosolar planets. So that's really what the scope of tonight's presentation is about. And we're going to be looking at four main categories here: wind, rain, lightning, and storms. Pretty simple outline. And when I was growing up, I used to watch science fiction movies. I think we all did. It was always fascinating. Star Trek. They would zoom around, land on an alien world, and they could beam down to the surface without any kind of protective covering. And the atmosphere might be a little different. You might have a reddish sky instead of blue sky, or you might have pink roses or daisies or whatever. But in reality, from a science fiction standpoint, they sort of portray other planets that are Earth-like as being very common in the universe. And we're not even close to discovering a world that's like Earth. I mean, we're coming close with Gliese 581. It's a water world. We'll talk about that in another presentation. But a lot of the planets that we're discovering out there are extremes compared to Earth, and they have extreme environments. So first up, let's talk about winds. What are some of the wildest winds in the cosmos? Well, Jupiter's jet streams, we'll start there. Jupiter has some of the most exotic weather patterns of any planet in our solar system. It's the largest planet by far. If you took the mass of all the other planets, all the other bodies in our solar system except the sun, and added them all up, Jupiter would have more mass. And it has tremendously extreme weather patterns. Thunder on Jupiter travels 4 times faster than it does on Earth. Rain falls twice as hard on Jupiter as it does on Earth because of the gravity. And you have cumulus clouds on Jupiter that are 30 miles high compared to 6 miles on Earth. But the biggest thing is you have multiple jet streams on Jupiter. Think of Jupiter's weather patterns as being like Earth's, only a lot more complex, and like Earth on steroids. So on Earth we have 1 jet stream per hemisphere. But on Jupiter you have about 30 jet streams per hemisphere. And our jet stream varies a lot. That's why our weather is usually different from year to year, because the jet stream is constantly changing. Well, on Jupiter you have a very stable set of jet streams per hemisphere, the bands and the belts that go back and forth. So you have about 30 jet streams per hemisphere on Jupiter. Each one of them, the atmosphere on Jupiter is about 1,000 miles thick as compared to Earth, which is about 100 miles thick. And you have wind speeds on Jupiter that are up to 300 miles per hour consistently. So it'd be a hell of a roller coaster ride if you got into one of these jet streams. You can imagine traveling at 300 miles per hour and then the altitude difference being over 100 miles over a period of several seconds. And the pressure extremes, if you were going through this experience, would be greater than going from sea level to Mount Everest over a period of a few seconds. So multiply that by several factors, and that's what it would be like to travel through Jupiter's jet streams. So Jupiter's jet streams have some pretty extreme weather patterns and some pretty wild winds. And really all the gas giants do too. When we're talking about winds in our solar system, Neptune is the planet. Neptune is the windiest planet in our solar system. And it's really interesting because it's so far away from the sun, and it receives so little sunlight compared to Earth. In fact, Neptune absorbs about 0.1% of the sunlight that Earth does. So it's really a mystery as to why Neptune is such a windy planet. And there are 2 theories behind this. One is that possibly the planet has a large internal heat source, because you need heat in order to generate winds. The other one is a lack of surface friction. So you can see the features here on Neptune from the Voyager flyby. Great dark spot, similar to Jupiter's red spot. It's about the same size as Earth. And you have wind speeds on Neptune in this dark red spot, or in this great dark spot, that travel about 700 miles per hour, right around the speed of sound. And on Neptune, the fastest wind speeds travel at about 1,500 miles per hour, or twice the speed of sound. So imagine standing outside and have a cool breeze like tonight blow by you, only several times cooler, and blowing twice the speed of sound. And that's what it would be like to stand on the surface of Neptune, if Neptune had a surface. So Neptune is a very windy planet. You can see here some of the wind, the cloud structures that are whipping around the planet really, really fast. Now, Neptune, because Neptune is not like Earth, it's a gas giant planet, so it doesn't have a lot of surface friction. You know, on Earth we have trees, we have cliffs, we have canyons, we have mountains. We have a lot of surface features that cause friction, which slow down our winds. And it's fortunate for us, because if we didn't have that, the winds would continue to speed up. That's what's happening on Neptune. That's why Neptune is so windy. Because there's no surface friction, over time these winds build up and they don't slow down. So the lack of surface friction is really what causes these winds to build up over time to tremendous speeds. So, but again, because it's so far away from the sun, because it receives so little sunlight, it really is a mystery as to why Neptune is so windy. But bottom line is Neptune is the windiest planet in our solar system. But as windy as Neptune is, and as powerful as the winds on Neptune are in our solar system, Neptune pales in comparison to the third category, and that is hot Jupiters. What are hot Jupiters? Hot Jupiters are a class of exosolar planets that orbit other stars. They just started being discovered. In fact, the first exosolar planet was discovered back in 1995. We're now getting to the point where our technology has advanced far enough where we can start detecting these things and actually imaging these things. And it's really interesting. Exosolar planets are gas giants, most of them, that orbit closer to their stars than Mercury does to the sun. That's why they're called hot Jupiters. And they're larger than Jupiter, and they receive about 20,000 times more light from their parent star than Jupiter does from the sun. And they have extremely high surface temperatures, 1,500 to 2,000 degrees Fahrenheit in a lot of cases. And this heat is what causes a tremendous amount of violent weather on these planets. One example is HD 189733b. And this is an exosolar planet in the constellation Vulpecula, 63 light years away. It's 13% larger than Jupiter, and it orbits only 3 million miles from its star. Now, Mercury is 36 million miles away. So compare that to 3 million miles for this hot Jupiter. It's larger than Jupiter, and it orbits only 3 million miles from its star, which means it can orbit its star in only 2.2 days. So it's 12 times closer to its star than Mercury is to the sun. So what happens? Now, one phase of this planet is tidally locked to its star. So the thinking is you have the day side and the night side, all right? The day side is tidally locked to its star, so obviously it's going to roast, it's going to fry. But what's happening on the night side of the planet? You would think that the day side would be really, really hot, and the night side would be really, really cold. However, that's not the case with this particular planet. What happened is scientists measured how much light is eclipsed from a planet as it passes in front of and behind its star as it's orbiting around, as this planet is orbiting around the star. And they did that to get an idea of how much heat this planet is giving off. And they found something very, very interesting. What they found was, this is an actual infrared image of this planet right here, HD 189733b, that was taken by the Spitzer telescope back in 2007. So this is the first infrared image of an exosolar planet ever taken. And what it shows is, yeah, on the day side of the planet, you have a lot of heat, a lot of thermal energy being given off. That's what we expect. But you also have that on the night side of the planet, which is very interesting, an tidally locked planet. Why is that? What's causing that? The night side glows very, very brightly in infrared wavelengths, which means there's a tremendous amount of heat being given off. So what's causing that? In fact, the temperature difference between the day side of the planet and the night side of the planet is virtually the same, even though the night side doesn't see the star. So what's causing that are extremely violent winds that are blowing the heat around the planet. In fact, these winds blow up to 6,000 miles per hour, 10 times the speed of sound on this planet. If you were to take a trip at 6,000 miles per hour, you could get from New York City to Los Angeles in 20 minutes. And that's what's happening on this star. On this planet. Exosolar planets are very, very violent in terms of their winds and their weather patterns. And this is transferring the heat from the day side of the planet to the night side. So, hot Jupiters, badass planets. Very, very powerful. So, the interesting thing about hot Jupiters, though, as we study them, is how can they form so close to a star? This thing is 3 million miles away from its parent star. How does a gas giant, 13% larger than Jupiter, form that close to a star? And the answer is, they can't. All right? In order for a gas giant like this to form, it needs to form in a region of its solar system called the snow line. Because what happens is gravity causes rocks and rocky bodies to coalesce into a rocky core about the size of Earth. And then the gases accumulate. That's how gas giants form. In order for that process to take place, it has to happen in a solar system where you're far enough away from the star where the radiation pressure isn't going to blow away the gases. So you have to be at about a distance from the sun to Jupiter, or about 5 times further away from the star than the Earth is from the sun, in order for a gas giant to form. So the bottom line is, what we learned by studying hot Jupiters and exosolar planets is planet formation is a very chaotic process in these solar systems. So it's like a gravitational musical chairs. What happens is you've got all this debris that's left over from the protoplanets and from the debris of disk from when the solar system is forming. And these coalesce into bodies, and they're orbiting the star, and there's like a gravitational musical chairs that takes place as these bodies form. And over time, what happens is the gravity will fling some of these objects out of the solar system, and also the gravity will cause some of them to get swallowed up by their parent stars. So you can have a large gas giant planet form out by the snow line, and depending on how chaotic that solar system is, gravitational forces will cause it eventually to move in. So that's how this hot Jupiter got there. It didn't form there, it formed out by the snow line, but over time, it migrated in really, really close to the star. It's a process we don't completely understand yet. That's the only logical explanation for how it got there. It could not have formed that close to the star. So, it's a very, very chaotic process, and it's very interesting to see how planets form. We're starting to learn this now. Planet formation it's not only chaotic, but it's very, very common. It's interesting where some of these planets are forming. They form in just bizarre places in the universe. So planet formation is very common, we're finding. These planets are monsters, but where they end up depends, it depends on a series of processes that scientists are still trying to understand. So hot Jupiters, very interesting. Let's talk about, yes?
What type of stars do they form around? Do they form any type of star? Or?
That's a good question. A lot of the stars that they form around are red dwarf type stars or yellow dwarf type stars like our sun. Mm-hmm. That's where we're finding them. So just average, ordinary, main sequence type stars, or even smaller dwarf stars that are dimmer and that give off less radiation even than our sun. Mm-hmm. So the place to look for, especially rocky bodies like our Earth, it's all about trying to find other Earths, right? Other planets like our Earth. We still don't know if Earth is a common occurrence in the universe or if it's a 1 in a billion freak. But the place to find those types of planets is around smaller, dimmer stars. So here's an interesting fact. You walk outside on a clear night, you look up, you see the Milky Way. You're seeing about anywhere from 8 to 10,000 stars if it's a really, really clear night. Most of those stars that you're seeing are going to be brighter and bigger than our sun. However, the vast majority of the stars in our galaxy and in the universe are smaller and dimmer than our sun. They're either red dwarfs or brown dwarfs. So the majority of the stars in the universe are actually really, really small and dim. Yeah.
Is there not a stellar wind, like there's a solar wind
Oh, absolutely.
that blows, that would blow it apart?
Well, yeah, that's the reason why we know that gas giant didn't form that close to that star is because the radiation pressure or the stellar wind from that star would have blown it away. The gas could not have coalesced around that rocky body to form that gas giant. It had to form out by the snow line and then migrate in over time due to gravity. So we know that it couldn't form that close.
Being that close is not enough for the stellar wind to blow
It is.
away.
It is. It'll blow it away over time. I'll show an example here in just a second. It's interesting. Yeah, it's a good question. Let's talk about rains, toxic rain. This is fun. So, rain on Earth is obviously water. It's not harmful to us in any way, shape, or form. But on other worlds, you have rain that's made up of very, very different substances. It can be very, very harmful. So, we talked about Titan, second largest moon in our solar system, Saturn's largest moon. Titan, those of you who heard my Saturn presentation last fall, we talked about this. Titan is the only other world in our solar system that has flowing liquids at the surface. You have Earth with water, and then you have Titan with liquid methane. So methane is a gas on Earth, but because Titan is so cold, minus 300 degrees Fahrenheit below zero, methane, which is a gas on Earth, actually liquefies. So you have terrain on Titan, which is very, very similar to terrain on Earth. In fact, if you had a webcam on Titan, you could think you were actually standing on the surface of Earth. You would see mountains, you would see cliffs, you would see canyons, you would see riverbeds, you would see lakes, just all this terrain that's formed by flowing liquids at the surface, which is liquid methane. So, and on Titan, you have a rainy cycle. You have a cycle of rain just like you do on Earth, only it's a methane cycle. So it evaporates, it forms clouds, and then it rains down. So you have liquid methane raining down on Titan. Only it's ice cold. These drops are bigger than ordinary raindrops would be on Earth. They fall much, much slower because the atmosphere is thicker and denser and the gravity is weaker. So it would almost be like being in a rainstorm where everything is in slow motion. So Titan, if you were caught in a rainstorm, it would be a slow, waxy drizzle with the consistency of crude oil, all at minus 300 degrees Fahrenheit. Basically, liquefied natural gas falling. Very, very toxic. So that's methane rain. Titan, fascinating world. But that's nothing compared to Venus. Venus is a very bad planet, which is why women are from Venus. Second from the sun, surface temperature about 864 degrees Fahrenheit. So hot enough to melt lead. You basically have a runaway greenhouse effect on the surface of Venus. And you have an atmospheric pressure that's 90 times greater at the surface on Venus than you do on Earth. So it would be the equivalent of being about 3,000 feet below sea level, or below the ocean. That kind of pressure is what you would feel if you were on the surface of Venus. You'd be squashed flat. And Venus forms what's called sulfuric acid rain. So you have all this volcanic activity that spews this ash into the atmosphere. And it forms these rain clouds about 24 to 30 miles in the upper atmosphere. So it rains sulfuric acid. Of course, sulfuric acid is very, very toxic. It's car battery acid. Now, the good news is it evaporates before it gets to the surface. So if you were lucky enough to be transported to the surface, you would be crushed to death and be burned to death, but at least you wouldn't be corroded by the acid rain because it evaporates about 19 miles above the ground. But still, sulfuric acid rain is very, very bad. And yeah, Venus is a fascinatingly hostile planet. When you think about how hot it is and how dense the atmosphere is, and then the fact that we have sulfuric acid rain clouds that are that when the rain is condensing and falling. It takes Earth, it's the extreme environment of what we would see on Earth. So that's sulfuric acid rain. Now, let's move on. We talked about hot Jupiters earlier. WASP-12b is a hot Jupiter planet that's orbiting a star in the constellation Orion. And it's about 600 light years away. And it's orbiting a star very, very similar to our sun. It's a G0 main sequence star. It's about 1.4 solar masses, 1.4 times larger than our sun. And the planet is also about 1.4 times larger than Jupiter. So you've got this star here. It's a G0 star, 1.4 times the size of Earth, or the size of the sun. And then you have this planet here, which is about 1.4 times the size of Jupiter. And it orbits its star in only 1.1 days, so it's very, very tight. And it's a carbon-rich planet. And what's happening is the gravity of this star is stripping material off of the planet. In fact, it sheds about 189 quadrillion tons of material every single year. And it's actually stretching the planet out, kind of an elongated shape, and stripping material out and forming a ring around the star. So it's called WASP-12b, and it looks like a wasp. It looks like a stinger. And it orbits about 44 times closer to its star than the Earth does to the sun. So it's being fried and stripped of its matter all at the same time. It's a carbon-rich planet, and it has an element in its atmosphere that's called corundum, an overabundance of corundum in its atmosphere. Now, what is corundum? Corundum on Earth is the main element that forms sapphires. All right? So sapphires, rubies, emeralds, these things. These things are made out of corundum, which is a solid on Earth. However, on WASP-12b, it vaporizes because of the heat. So what's a solid on Earth is actually a vapor on some of these hot Jupiters. So what does that mean? It means that on WASP-12b, you have what's called sapphire rain. So you have molten raindrops made out of molten sapphire on WASP-12b. And you can imagine what that might look like. How many of you in here have ever got caught in a rainstorm of molten sapphire? Hasn't happened to me either. You need a special type of umbrella to survive. So molten sapphire rain on WASP-12b. This is the kind of stuff that we're discovering now because of advanced technology. Yeah.
Is there other planets besides this planet that circles that sun? Do you know how many planets?
In that system, I don't know. I mean, these types of systems are becoming more and more common. We're finding more and more of these hot Jupiters that orbit really, really close. In this particular system, I don't know if there's another one or not.
No, okay.
So, yeah. But anyway, yeah, on hot Jupiters, what's a solid on Earth vaporizes and forms rain clouds, and you get this exotic rain. But the baddest rain in the universe is by far brown dwarfs. Brown dwarfs are failed stars, okay? They're like Jupiter, they're larger than Jupiter, but they're smaller than the sun, which means they have a lot of mass, and gravity started to form them into a star, but they just didn't have quite enough mass to actually undergo thermonuclear fusion in the core and get to a point where you have hydrostatic equilibrium, where the star is fusing hydrogen into helium, and you're in equilibrium between the forces of the star that want to blow it to smithereens because of the radiation pressure and the gravity that wants to crush it out of existence. So that didn't happen here. You basically have kind of a cross between a planet and a star. You're somewhere in between. That's a brown dwarf. So the surface temperatures, though, on brown dwarfs are very, very high, about 3,000 degrees Fahrenheit. And what's interesting is you have iron as one of the elements that makes up brown dwarfs. And like WASP-12b with corundum, iron vaporizes and forms rain clouds on brown dwarfs. So what you have is molten iron rain. on brown dwarfs. So here's the situation. You have a temperature of 3,000 degrees Fahrenheit. Iron vaporizes, forms clouds, rises up, cools, and forms these really, really toxic, deadly raindrops that are like sand that's being pelted out of a sand blaster. Because brown dwarfs have a lot of mass, they have high gravity too, a high gravitational field. So these raindrops are falling really, really fast. Molten iron rain falling at 100 miles per hour at a temperature of 2,800 to 3,000 degrees Fahrenheit. That's what's going on right now all over the universe in brown dwarfs. So you can have a little bit of fun with this. You can imagine what would happen if this happened on Earth. You walk out one night after work and you see these molten raindrops of molten iron falling down, hitting everything at 100 miles per hour at a temperature of 3,000 degrees. That would not be a good day. So molten iron rain is the most abundant rain in the universe. And you guys thought it was liquid water, didn't you? Molten iron rain, because brown dwarfs are the most common types of stars, along with red dwarfs in the universe. Yes?
Was a brown dwarf, was it ever a red dwarf? Is it?
No.
So, okay, so
It
it's
had
not
enough
in the
mass.
process of turning into a black hole at any point or anything like that? Okay.
To get to a black hole, you need to have a star that has, it's like Deneb, well, Deneb will probably become a black hole. You need a lot of mass.
Okay, okay.
And then it'll eventually go supernova, which means it'll blow itself to smithereens. And then you need a stellar core left over after the supernova event that has somewhere between 1.4 and 3 solar masses. 1.4 solar masses is the Chandrasekhar limit. So we know if it's more than 1.4, it'll become a neutron star. If it's 1.4 or less, it'll become a white dwarf. So our sun will become a white dwarf because it doesn't have enough mass. But yeah, brown dwarfs are just basically failed stars that just didn't have enough mass to form a star.
Were they ever any point another class of star before they become brown dwarfs, or?
No, they're
They
basically,
just,
yeah.
instead of turning into a star, they just turn into a brown dwarf?
They have more mass than Jupiter, so they're a step above Jupiter in the formation, in the process of becoming a star, but they don't have enough mass for the gravity to crush the matter together where you have thermonuclear fusion taking place.
Okay.
So it's basically just a failed star. But it's an interesting hybrid because you have a lot of temperature and you got some interesting environmental conditions on brown dwarfs, but it doesn't glow. I mean, it doesn't emit light like a star would.
Okay.
Okay, let's talk briefly about lightning. So we have lightning on Earth. Saturn has a band of weather in the southern hemisphere. We call this Storm Alley, just like we have Storm Alley on Earth. Scientists are now really beginning to study the surface of Saturn as a result of the Cassini mission. So you have eddies, plumes, ovals, weather patterns on Saturn that are very similar to what's going on Jupiter. In fact, Saturn, in a lot of ways, is just as dynamic, if not more dynamic than Jupiter is in its weather patterns. So when you have storms on gas giants, they can last for months or even years, and very, very violent storms. So lightning on Saturn is very, very powerful, 1,000,000 times more powerful than lightning on Earth. In fact, in November of 2009, Cassini observed a lightning storm where the bolts were half the width of the state of Arizona, and the electricity that was unleashed from one bolt would be enough to fry the entire state of Tennessee. And this lightning storm lasted for 8 months. So when these storms form on gas giants, they go for a long time. Not only windstorms, tornadoes, hurricanes, but also lightning storms. So very, very powerful lightning on the surface of Saturn. Let's talk about storms. Saturn, speaking of Saturn, in the south polar region, we have discovered a hurricane-like storm that has a clearly defined eye wall. It's the only other storm in our solar system besides hurricanes that form on Earth that has a clearly defined eye wall. So it has a hurricane-like structure. Winds are blowing counterclockwise at up to 350 miles per hour. The clouds rise 20 to 45 miles high. Compare that to 5 miles on Earth. So it's a huge storm, and it's 5,000 miles wide. on Saturn. It's been there for a long time. So to put that in perspective, imagine a hurricane with a clearly defined eye wall blowing at over 350 miles per hour that stretched from New York City to Baghdad and annihilated everything in between. That's what it would be like if this storm formed on Earth and was there for years. Very, very powerful storm on the surface of Saturn. Venus. Let's talk about Venus. Venus has a very interesting double storm in its south polar region. It's called a double vortex. It's like a twin tornado. In fact, it's an upside-down tornado. So what you have here is you've got two storms that are like upside-down tornadoes, and they're a permanent fixture in the south polar region. And what they're really doing is acting as a funnel to transfer heat, because the planet is so hot. It's like heat from the equator of the planet is radiating out and then transferring to the polar region, which is a little bit cooler. And that's the source of these storms right here. So it's similar to like when you fill up your bathtub and you drain it, and then you got that swirling motion. Same type of thing is happening on Venus in the atmosphere with these storms. We don't understand why it's a double storm, a double vortex that's forming. But these storms are thousands of miles across, and the wind speeds are hundreds of miles per hour. Extremely violent, and they're a permanent fixture. They've been there for a long time, and it's going to stay there for a long time. So this is another feature, another noticeable feature on the planet Venus. This double vortex, this south polar double vortex. Very, very powerful storm, as a result of the internal heat of the planet. And of course, the number one storm in our solar system is Jupiter's Great Red Spot. It's an anticyclonic storm in the southern hemisphere. It has a period of 6 Earth days. It's about 2 to 3 times the size of Earth. It's 350 years old. We first discovered it, Galileo did, and he pointed his telescope at it back in the 1600s. It's still there. We've seen other storms like the Great Red Spot form on Jupiter. And then some of these storms emerge, some of them die out. So, wind speeds up to 350 miles per hour, 8 kilometers above the, okay, so the storm itself seems to be cooler and less violent in the center than around the edges. So around the edges of the storm is really where the most violent activity is occurring. And we think that the source of the Great Red Spot is internal heat from within Jupiter trying to escape, forming almost like a large volcanic structure, where you have a huge swirling storm where this heat is trying to escape, and that's what's causing the storm to form. But why it's been there so long and why it's been stable for so long, we don't completely understand. Jupiter's atmosphere is very, very complex. And scientists have been studying it for years, learned a lot, but there's still a lot more to discover about Jupiter. But it is, in terms of weather, if you're into weather on other worlds, Jupiter is the planet to study. So, yeah, by far the largest and most intriguing storm in our solar system. So,
Stay in the same place?
it moves. It moves across the banding structure. So we talked about this. I didn't put this slide in this presentation, but yeah, it does. It has a period of 6 Earth days where it moves across and then moves back. So depending on the movement of the jet streams in those 2 bands, the storm actually moves. So it doesn't stay in one place. The storm itself is stable, but it moves across the planet. All right. So to summarize, obviously Earth's weather is nothing compared to weather on other worlds. The average wind speeds on Earth are about 25 miles per hour. You compare that to what's going on in the gas giants in our solar system, where the average wind speeds are about 250 miles per hour, 10 times greater than they are on Earth. And then, of course, hot Jupiters, where you're up to 6,000 miles per hour, or 10 times the speed of sound. So the winds on some of these alien worlds are extremely powerful. Well, what's interesting is as our technology improves, because of the Hubble Space Telescope, and now we're working on a telescope, scientists are working on a telescope that's going to be even more powerful yet. We're able to see out there and discover these exosolar planets, image them, and study them, and really get insight into planet formation. It seems to be a more common process than once thought of in the universe. Planet formation, the process, the planet formation itself is something that seems to happen pretty regularly. But we still don't completely understand all the reasons why certain planets end up where they are and the forces that bring them there. So it's still a work in process, it's still a work in progress. So it's an interesting topic because it's where astronomy gets really, really fun, really, really interesting, but the science behind weather and other worlds also helps us better understand how certain planets form and how certain solar systems form. So that's why this topic is interesting. For me, it's just fun to see what's going on and compare it to what's going on Earth. So anyway, that's my talk. So thank you.
You give the orbit distance from the planets, is that from the center of gravity of the planet, or is it from the surface?
Oh, that's from the surface.
From the surface. I would assume that these orbits, as they have been moved in from some unknown thing happening, are probably very eccentric.
What was causing the planets to move in?
Eccentricity of the orbit is probably pretty high, right?
In some cases it is, yeah. In fact, there's one exosolar planet. A lot, when you study planets, most of them have a fairly circular orbit. But there are some exosolar planets, I'm trying to think of one in particular, I didn't put it in this presentation, where it has an extremely elliptical orbit. In fact, it varies from 3,000 or 3 million miles to its star to as much as 75 million miles. And that has a very intriguing weather pattern because when it's way out here, 75 million miles away, it's cooler. But then as the planet approaches the sun, you see this star getting bigger and bigger on the horizon, and it literally causes a shock wave of heat and weather around that planet. So I didn't put that in this presentation, but that might be a topic, something to put in a future presentation, because that is a fascinating world to study, the weather pattern on that world. Because you literally have a shock wave of heat and wind that just screams around the planet as it gets closer to the star. But yeah, it swings around in a huge loop. So some of these exosolar planets have really strange orbits.
If they have a magnetic field, it would seem like it would be one heck of a bow wave.
Yeah.
It would be pretty spectacular.
Yeah, it's interesting. So, any other questions? Yeah.
You said that the planets seem to be like a regular thing where they do. I'm assuming they haven't actually witnessed a planet being created at this point.
That process takes
I'm
place
assuming,
over.
right, and that's what I was assuming. So
Yeah.
I was just wanting to make sure that was correct. That I hadn't missed something that.
Well, there's a lot of reasons. We're finding just some of the strangest planets out there. To me, the strangest planets that I think have ever been discovered are pulsar planets. You have 3 rocky bodies, 2 of them the size of Earth and 1 of them the size of Mercury, that are orbiting around a pulsar. How do you get planets around a pulsar? A pulsar is the remnant of a supernova. So they could not have been there before the supernova occurred because the supernova would have blown them to smithereens. So they had to have come there after the supernova event occurred and the pulsar actually was created. So the existence of those types of planets tells us, as well as some of these hot Jupiters, we have these large gas bodies like we talked about that are really, really pulsar stars, tells us that planet formation has to be fairly common. And there are forces that maybe we don't completely understand yet that are bringing these planets around these stars. So there's just some really strange stuff out there.
Yeah, there's a story on the news just today about, they think they have imaged a planet forming around another star now. I don't remember what star it was, but it's out as far as the Kuiper Belt, which is very unusual. But they said the problem is they have to give it more time because they're not sure if it's just a distant background object.
Right.
Right, but, so that was just on the news today.
That's
And maybe the first one they've imaged where it's actually in the formation stage.
Oh, okay.
Okay,